All right, let's look at some more examples. A laboratory has 500 milligrams of an exponentially decaying material. If 390 milligrams of the material remains after 7 days, how much remains after 30 days? So let's identify the type of problem. This is an exponential decay problem. It's also a point problem because we are given point data and no rate data. So if I'm given a bunch of points, I'm probably going to use exponential regression to do this. And that is what I'm going to do. So let's call up the calculator. Let's go ahead and just clear your list because I know there's stuff in there that I don't want anymore. We start off with 500 milligrams at times 0. Your first column is always going to be your times. And then after 17 days, we have some other amount. Okay. Let's go to column 2. So we begin with 500, and then we go down to 390. Then do exponential regression. There's our model. The question actually asks just for how much is going to be there after 30 days, so I know already. I just need to go to a vars y vars function and put in 30. And there's our amount, 322.514. Okay, so this solution uses the 2-point model, which is absolutely fine. I just used exponential regression instead. All right, moving along. On April 26, 1986, there was an accident at the Chernobyl nuclear plant in the Ukraine. Among the results of the accident, approximately 2.7 million curies of radioactive cesium-137 was released into the environment. This radioactive isotope has a half-life of 30.17 years. How much remained on April 26, 2018? Okay. So this is very similar to the problems that we've done before. In fact, let me just go back and remind you. Where was the last one we did? Here we go. We did a problem earlier where we actually were given the half-life and then found the rate. And how did we do it? We used exponential regression. So that's what we would do here as well. I'm just reminding you of your technique. I'm going to use exponential regression where my time is going to be times 0 and time 30.17. That's my half-life. And then my initial amount, let's say it was 1 unit, 1 curie. Oh, I'm sorry, we actually had an initial amount, my bad. So let's call that 2, sorry, let's just erase that. 2.7, and then this, what would go here would be just this number divided by 2. So you can literally just type in 2.7 divided by 2 into the entry, and then you'll do x per egg, and then that's going to give us our model. And then once we have the model, we can answer this question, which wants to know how much remained on April 26, 2018, which is just a calc or a vars y vars question. And you should get 1.29 million curies for that. All right, so I'll let you work out the details of that one since it's pretty similar to what we've done before. How about something like this? So I've been using exponential regression. What if you're just given something in the 2-point form so you don't have a choice and you kind of have to use this form and you want to find the growth and the decay rate? So that's kind of a weird question, but how would we handle it? Well, the key here is to isolate the factor. So what is the factor? because we use the factor to get the rate. And the factor, what I'm going to do is kind of rewrite this. And all I've done is separate the variable from the other portion of the exponent, because the other portion of the exponent is actually part of the factor. So the factor is all this stuff right here. So the factor is, and I left out the initial value and I left out the variable, but not all of the exponent, just the variable part of the exponent. So the factor is 139 over 96 to the 1/8 power. And so I need to get the rate from that. So how do I do it? Well, calculator, whoops. And I would use a lot of parentheses here, personally. Okay, and that is my factor. So we are actually looking at a true growth model. So this is actually growing, and I know that because 1.04 is bigger than 1. So this is equal to let's call that 1.047. So this is the growth factor. And therefore my growth rate is 0.047, etc. So this number minus 1. And in this case, I actually do have a true growth rate. So that's 4.74%. And then my decay rate, now here's the one case where actually I'm going to have a negative decay rate. This is sort of a weird question, though, to be honest. You won't see stuff like this too much, but we do actually have a negative decay rate here because we are actually growing. Okay. Here's a financial question. A bank offers an annual rate of 2.8% compounded weekly. So we're back to weekly compounding. If $1,090 is deposited in the account, how long does it take to get to $1,800? All right, well, let's first write our model down. Oh, by the way, we're pretty much just reviewing now. So, we're going to be talking about exponential growth functions, exponential decay functions, all of it all mixed up together. So this is not specifically, as you saw from the last example, this is not just decay. This could be growth or decay at this point. So, you have to pay attention. So this is a growth model. So my exponential model for compounded growth is initial value 1 plus 0.028 over 52. I'm making that 1 big so you don't accidentally put it in the fraction. And this is raised to 52 times t. So that will be my model. I want to get to $1,800, and so y2 will be 1,800. And this is going to be a calc-intersect question. Here you have your solution, t equals 17.92. I'm not going to go into the details of this one either because I feel like this is a pretty straightforward problem. But I think the difficulty is in just remembering what to do. So hopefully I've kind of reminded you of the necessary equations for this. Okay. How about this one? A bank offers an annual rate of 2.8% compounded weekly. What is the account's effective annual yield, so the EAY? This is the one we just did, by the way. So we can just go back here, and if you remember what is the EAY formula? Well, it's the factor minus 1 times 100. So EA, I'll just write it here. The times 100 is to put it in percent form. And that's the formula. So really we just take this value, subtract 1, and then multiply by 100. And that's what you see right here. So notice that the EAY in this, once you do the computations, your actual EAY 2.83 or 2.84 approximately percent is bigger than the APR. That's because we're compounding weekly, and so effectively we're doing better than 2.8% compounded annually. We're doing 2.8% compounded weekly. Okay, so it's a little bit better. All right, moving along to more growth and decay models. What happened? How do you handle a question where you are given a doubling time, and then we want to know something about the model? Okay. So if I know the doubling time, I can use exponential regression to get the model. So when you're given the doubling time, because what I can do is write down that would be 2,240. I can enter my data. I have 2 points, and then I can do exponential regression with this data, get the model. That'll give me my model. And then once I have it, I can use the model to find this, that's an output of the function, so this will be a calc-intersect question. Ultimately, I mean, first it's exponential regression to get the model, and then calc-intersect to actually find the solution, which is 11.08 days. Let's do another one. If the per unit growth factor for a quantity is 1.0075, what is the quantity's per 5 unit growth factor? Okay, so now we're getting really weird. This is about a factor, not the rate, but we're changing the unit. So it seems weird, but it's actually going to be kind of easier in a sense. The 1.0075, well, let's just dive into it and we'll see. So what does all this mean? We know that B equals 1.0075, and then I want the 5 unit growth factor, so I just need to take that value and raise it to the 5th power, and essentially that's it. That is all we have to do here, because it doesn't ask for the rate, it just asks for the factor. And that is 1.0381%. If you did want the rate, we could get it. That's what's happening down here in this asterisk area. We get this value and then subtract 1 from it and multiply by 100. And so 3.81% is your 5 unit growth rate. All right, let's see if we can squeeze another problem in here. What's the half-life of a quantity that decreases 7% weekly? So by the way, if we're given a weekly rate here, then our half-life is going to be in terms of weeks. But so my rate is 7%. So my model is going to be, let's assume we start off with 1 unit. That's going to be 1 minus 0.07 to the t. That will be my y1. And then my y2 will just be 1/2, and then I can do calc-intersect. Okay, I think I'm about out of time in this lecture, so let me just quickly run to the answer. That's 9.55 weeks. As I said, it's in weeks. So I know I didn't really go into the details, but that's essentially how we would approach it. Okay, I'll pause here.